All right. So we're moving into 2.5. We're going to be talking now about the different hemispheres of the brain. We've talked a little bit about this already. For instance, you know that the brain hemispheres are contralateral, meaning that each side of the brain controls the opposite side of the body. It's going to be important in a minute as we start talking about things like split brain patients. So let's go over a couple of the interesting things about hemispheres. This one should be pretty quick. So, left and right hemispheres of the brain, and they are connected by these series of nerves known as the corpus callosum. These are nerves that connect and allow the left and the right hemispheres to communicate, because without the corpus callosum, it's basically two different brains. Right? They are entirely separate, except that they can communicate to each other. It's like two different computers that are connected by wires. Right? They're both processing and doing their own things, but they are able to communicate and talk to each other. So each hemisphere receives information from and controls the opposite side of your body. And there are certain things that each of them specialize in. A lot of them are doing the same thing. They're both moving portions of your body. They're both processing vision and hearing, and sensations, but they're also doing some specialized things, right? And we've talked about some of that, like Broca's areas, Wernicke's area, the fusiform gyrus. Like those are very specialized portions. And on top of that, there's other little things that each side is slightly better than. So, for instance, the right side of our brain is going to be much better at spatial things, right? It's oftentimes when people say that they're very right-brained, that often referring to someone who's very artistic, right? They're oftentimes more abstract, creative. The right side of the brain, and we know this again through PET scans and functional MRIs, we can see that side of the brain begin to light up more, use more glucose, whenever it's doing more imaginative work, whenever it's doing things that are much more spatial, right? When it's trying to gather context, determine abstract meaning. Okay. The left side of the brain, however, is always, and this is probably the biggie that you should know, related to speaking, right? The Broca's area and Wernicke's area are both in the left side of the brain. All speaking is processed in the left side of the brain. It also works in our ability to read, write, listen, grammar. All of our language happens on the left side of the brain. The right side does deal with language to some extent, but interestingly enough, it kind of just helps us a little bit with almost the context in which we use things. I think the textbook uses the example of like helping us with cadence, right? Whenever we're using sentences and the way that we say things out loud, implying a comma in there, for instance. So saying something like "Let's eat, Grandpa," compared to "Let's eat, Grandpa." Like they both have very different meanings based on just the inflection of my voice. So right is kind of like a regulator to some extent, but it can't of its own fruition speak, right? It just kind of gives more space and context to the way that we do the things here. Left is a little bit more mathematical, computational, analytical, reasoning and logic, sequential thinking. That's very much left brain. So left brain is more like math and analytical thinking and speaking. Right brain, much more abstract, imaginative, creative, stuff like that. Biggies to know that will be more likely than not to pop up is that language in the left hemisphere and facial recognition is in the right. So, some of the pieces that are controlled in there outside of those, you'll see, for instance, one of those that you really need to know is thinking about the eyes, which I think are just a little bit different than everything else, right? So it's not so simple that the right eye goes to the left brain. Both eyes send information to both hemispheres, but both eyes both have a left and right field of vision. That's how we are able to process depth. It's how we recognize some objects are further away or closer than each other, right? It's how we kind of have this hand-eye coordination. So what's happening there is the left and right eye are both picking up two different fields of vision, and they're separating Okay, through that optic chiasm, you see that like split here jumps across to the other side, and then the two sides of the brain deal only in one of the fields of vision. So left side brain deals with right field of vision, right side brain deals with left field of vision. Okay. Other kind of specialized things, right? Know the fusiform gyrus that the right side does. Does the ability to recognize faces. Left side deals with like Broca's and Wernicke's. So those are probably the biggies, right? And then if we're controlling, do know that the right hand and right foot or right legs, right side of the body in general, is controlled by the left hemisphere and vice versa. Um, Probably most interestingly enough in the hemispheres is thinking about our patients that have split brain syndrome. This is pretty rare anymore, but in the 90s, it was relatively common to cut through the corpus callosum and separate the brain to fix epilepsy. So what you would often see is a brain that could no longer communicate with each other. And remember, right, going back here, the two sides of the brain do different things. They control different sides of the body. Our left and right hand need to be able to work together. And when you cut the corpus callosum, now we've got two different brains. To some extent, we have two brains operating kind of on their own. And for most people, this happens when they're a little bit older and they learn to function just fine. But it still can be very, very weird for a lot of people. So most famously, this study was done where they had someone with split brain look at this red dot and then they would quickly flash a word, right? They would flash a word for like half a second, which is more than enough time to recognize it for the human eyes and the human brain to process it. And so they would look at it, they would see the word heart on the screen. He on the left side of the red dot, art on the right side of the red dot. And then the doctor, professor, psychologist, whoever it is that's performing the study, the researcher, would then tell the person, like, all right, tell me what you saw. What would they say? Think about it. All right, so hopefully you could remember that all of our speech is located in the left side of our brain, meaning that the left side of the brain, which processes the right side of our vision, is going to say, I saw the word art, because that's what it thinks it saw. Okay, that shouldn't be too shocking, right? We saw the whole word, right? We saw heart. The whole thing was processed, but the left side of the brain is the only one that could speak. The right side of the brain was not able to process the word art. It only saw the word he, but the right side brain can't speak. So the right side brain could not tell you what it saw. However, when it gets really interesting, is when they then told the person, okay, so you told us that you saw the word art. How about you point with your left hand? What word did you see? What do you think they pointed at? They pointed at the word he, because our left hand, our left side of our body is controlled by our right brain, which can't speak, but it controls our motor cortex, and it points at the word he. Now, the crazy part is the left side of the brain at this point in this study, the people were shocked, right? The left side of the brain would always say, but I didn't see that. And it would quickly try to either say, it's like, I didn't see that, or it would rationalize it and come up with some crazy answer. There's all kinds of other studies that are done with this where they flash a word only to one side and they say, use your left hand to pick up what you saw. And you would out loud say, well, I didn't see anything. It was like, well, just try it. And you'd pick something up. And then they would ask you, why'd you pick that up? And they would make up an answer. The left brain would just make something, right? And that, because that's kind of what humans do. Our brains are able to make things up to protect us, our perception of reality to some extent. So the two brains, even though they can't communicate, we find ways to protect ourselves, and ultimately they work together enough to get us through, and it's better than the living a life with kind of intense epilepsy. So final thing for this topic is how we're processing information within the outer portions of the brain, how we're processing conscious and unconscious thought. And it's this idea of dual processing. Okay, so dual processing, other ways that you'll hear this if you ever see the book Thinking Fast and Slow. This is some of the famous work of Daniel Kahneman, who taught people, came up with this idea of system one and system two, also known as parallel and sequential processing. And these are the two different ways that we're consciously processing information. Our brain is always doing two things at once. So we are doing things, kind of this parallel processing where our brain is doing 1,000 things at one time. We're putting away subconscious information, and we're also able to do all kinds of things without consciously thinking about it, right? Think about like whenever, for those of you old enough to drive, you get in the car and you drive to school. You aren't like thinking about that. When I get in the car at 6:30 in the morning and I drive to school from here, I don't think twice about it. I don't even know the names of some of the roads I'm on probably. I just like know how to get there. I just go. That's parallel processing at work. Right? I know I see a stop sign, I slowly slow down and then I turn. I don't think, and now I should press the brakes. And now I should rotate the wheel 45 degrees so that I can turn right. And now I will rotate the wheel. My body just does it all. And this is kind of parallel processing. A lot of this is processed in the cerebral cortex, but also in the cerebellum, kind of in that like mini small brain in the back. But a lot of this is subconscious processing. And a lot of psychologists think around 90% of what we do is actually this kind of parallel automatic processing that is basically the same thing as what animals do. Right? They're processing things automatically. They're just reacting to things. And what we're really good at as humans is explaining these things as if we had done it with our own free will. Right? What we do have that animals don't have is we have this system two of sequential processing that gives us this more focused, conscious, problem solving processing that allows us to slow down. It takes a really long time. Right? It's going to be way slower to do anything, but it allows us to think creatively. It allows us to solve problems. It allows us to get things right, right? Because this parallel processing is really fast, right? It's like automatic. Our brain makes connections just automatically all the time in an amazing way, but it can be prone to errors. So really quick, I want you to answer this question in like 2 seconds. If a baseball bat and a ball cost a total of $1.10 together, the bat costs $1 more than the ball. How much does the ball cost? You probably got it wrong, right? You probably quickly jumped to the conclusion that the ball was, or that what is the question? The bat cost $1 more than the ball, and how much did the ball cost? Everyone always says $1.10, right? Or the ball cost 10 cents, right? If that were the case, it would cost $1.20, right? That doesn't work out, right? We would need system two to slow down because our common sense gets in the way and we do this wrong, right? We process this information way, way too fast. Whereas the right answer, give me a second, I'm going to have to think about it because, again, my system one is really, really slow. Or really, really, it's like quickly jump to conclusion, and system two is going to be slow. So we've got $1.10 total. Costs $1 more than the ball. How much does the ball cost? So the ball would cost 5 cents, and the bat would be $1.05, and they'd combine together to make $1.10. Right? System two takes a while to do that. Right? My brain's also working slow because it's a little late at night. But system one quickly thinks it has the answer, but it did it poorly. Right? If we sit down and think about it, we'll get it right. But our brain doesn't want to do that. Right? We want to get the answer quickly with parallel processing because, again, that's what our body wants us to do. But we have to often think manual override this like automatic drive that we're running on and then say, hey, no, let's take our time on this. So hopefully you all are pushing for a little bit more sequential processing in your studying of AP psychology work. So I will leave you to that. Get after it. We are ending this unit. We've got one more of these to go. So with that, I will bid you adieu and much love, fam.